All right, this video is designed to review the three major types of research designs that we are looking at in psychology class. All right, the first of those, the true experiment. I'll remind you what the components of a true experiment are. For true experiment, you have to have two or more groups with participants assigned at random. The reason we assign them at random is to assure that the groups are as similar as possible to each other before the study began. It does that because random assignment is the best way to minimize confounding variables. So, you remember how in lab for our first experiment, I had you roll the dice to determine which group you were going to be in. That assured us that they were random assignment. Then the experimenter assigns each group to one level of the independent variable. Remember, the independent variable is defined as the thing that is manipulated, the variable that is manipulated the way the two groups are treated differently. So in our lab experiment, this means the two groups got different instructions to count the vowels or to rank usefulness. Other examples of independent variables, if you were doing a drug study, you'd have a drug group and a placebo group. The independent variable would be drug condition, the levels would be drug and placebo. If you are going to study course delivery systems, you could randomly assign one group of students to take an online course, the other group to take an in-person course. That would be your independent variable, and those would be your two levels. So, independent variable is that which is manipulated. So after you do the manipulation, you measure your dependent variable. Our dependent variable in our lab study was memory, or memory, operationally defined as number of words remembered from the list. In another study, you could be measuring activity levels, sleep levels, scores on a math test, scores on some other test, anything that you are measuring. Then you do statistical analysis to determine if the groups are significantly different from each other. And depending on what statistical test you're doing, the criteria may be different. We remember the criteria in our lab study where it was if they were more than one standard deviation apart. But again, what this significantly different means are the differences between the two groups big enough that we say, okay, this is not due to random chance. This is not due to random error, that there probably really is a true difference between these two groups. If so, and if we've done our experiment well, we would hopefully be able to be reasonably confident that that difference is because of the independent variable. It's because of the manipulation. So, true experiments are really sort of the gold standard of studies because they are done well, the best controlled studies. What makes a good experiment? Well, you try to treat the two groups as similarly as possible other than the independent variable. For instance, let's say you were doing a study that required you to inject your one group with a drug. Instead of just taking the second group as your control group and doing nothing to them, you would ideally give them a control injection. Give them an injection of plain saline or plain water to do two things. First of all, that controls for placebo effects. The people don't know whether they've had a drug or not, so hopefully their behavior would not be changed by simply thinking that they might have had a drug. Secondly, it also controls for things like the stress and the pain of the injection, in case that would affect your outcome. So that would be the same with the two groups. If possible, you'd like your study to be double-blind. Now, double-blind means that participants should not know what level of the independent variable they're in, Ideally, they shouldn't even know what the purpose of the study is. Now, if you've reviewed the experimental ethics video already, you know we do actually have to tell them something about that. So you have to balance that with ethical concerns, and particularly the need to let your participants give informed consent, but keeping them as ignorant as possible about what is going on, about what you're looking for, what your hypothesis is, which group they're in, is going to minimize placebo effects. It's also going to minimize reporting bias. Keep them, if you're trying to measure their attitude, say, towards something, it keeps them from saying what they think you want to hear. That should, if they don't know what the hypothesis is, they don't know what group they're in. But by double blind, we also mean that the experimenter, ideally, should be blind, should not know what level of the independent variable the person is in when they are measuring, or whoever is recording the data. That could be, of course, the experimenter's student or an assistant of some sort, or whatever. So it's very common, for instance, if you're doing some sort of behavioral test, to have a student or an assistant actually do the manipulation and then have someone else test them who doesn't know what manipulation they got. That minimizes observer bias. So just like people can have placebo effects, if they think they have taken a drug, they may act like they have taken a drug. If a researcher believes, okay, I think antidepressants are effective, and I know this person's taken an antidepressant, and I've got to subjectively evaluate how depressed I think the person is, well, that could introduce bias on my part. I may see what I want to see. And if I don't know whether the person's on the antidepressant or not, then that can't be an issue. So, the question of causation. In a true experiment, like I said, true experiments are kind of the gold standard. They're the best controlled type of study. So you can be most confident that your IV manipulation caused the difference in the dependent variable if in fact your groups wind up significantly different from each other. But being most confident is not the same as being absolutely confident. The results are not conclusive proof. There is always a possibility that some unknown confounding variable that you are not aware of, something that you either accidentally manipulated something else along with your independent variable, or that purely by chance you wound up with one group significantly different in some ways, despite your best efforts and despite random assignments. I remember one year in Psych 101 lab when we were doing the descriptive statistics lab and the Val usefulness exercises, I happened to have 3 international students, a couple from Japan and one from Korea, who were in the class, and for all of them, English was not their first language. So there were some words on that list that they did not recognize. Well, purely by coincidence, all 3 of them wound up in the same group. So if the fact that English is not their native language, you could certainly expect that to affect the usefulness group. May not necessarily affect the vowel group, but it could affect the usefulness. That is a potential confounding variable that occurred despite every effort, and just because 20 students, 3 of them are international, by pure chance, all 3 of them wound up in the same group. So unlikely that will happen, but it's always possible. This is why researchers are very reluctant to use that word proof. We actually don't like that word. We prefer to say things like the data supports the hypothesis, or the data is consistent with the hypothesis, not the data proves the hypothesis. So that is a true experiment. Now, sometimes there are independent variables or factors or things that could influence behavior that you can't test experimentally because it is either impractical or unethical to manipulate that particular variable. For instance, sometimes you might want to compare, let's say, smokers versus non-smokers. There are enough known dangers of cigarette smoking that no ethics committee is going to let you ask someone who is not smoking to begin for the sake of the experiment. They're very likely to get hooked on cigarettes and not be able to stop, and that will be detrimental to their health. That is going to do harm to them. You simply wouldn't be allowed to do that. Let's say you wanted to study women at co-ed colleges versus single-sex colleges. Okay, it's not necessarily unethical to manipulate that, but it's really not very practical either. You're unlikely to find a bunch of high school seniors who are willing to be randomly assigned to a college. Maybe if you paid the tuition, they'd be willing to be in the study and for the sake of, but then you've got a very expensive study that I doubt any granting agency in the world could fund. So it's just not practical to be able to randomly assign people to attend a co-ed college or a single-sex college. Suppose you wanted to compare married women with unmarried women. Even more difficult. You're not going to be able to randomly assign some of your women to get married, some of your women to stay single for the duration of the day. They're not going to let you make that type of decision about their lives. And the most common type of this study is men versus women. Obviously, those are not conditions one can randomly assign people to. Gender is something the participants come to you already with. But you can actually, even though you cannot assign these groups randomly, you can recruit groups or find groups that are already categorized and measure whatever it is you're interested in and do the statistical analysis. So I could go out and recruit a group of students who already smoke and a group of students who are non-smokers. I could go out and administer a survey to women in a co-ed college and women at a single-sex college. I could do interviews with married women versus unmarried women and collect my data that way. And of course, there are many, many tests that test men versus women in all sorts of areas. So this is called a quasi-experiment. And by quasi, it's not quite a true experiment because the participants are not assigned at random. They have sorted themselves into the groups. They have not been sorted at random by the experimenter. So, although these can be very good studies, there are some concerns as well. So what makes a good quasi-experiment? Well, like with the experiment, it's good to try to find groups that are as similar to each other as possible, except for this quasi-independent variable. Okay? So for instance, if I was doing a comparison of single-sex college women with co-ed college women, and I was, for convenience, picking my single-sex students from Mary Baldwin. If I'm looking now for a co-ed school to recruit the rest of my participants, well, ideally, I would want to find a school that looked as much like Mary Baldwin as possible, but was co-ed. So I try to find a small school. I try to find a private school. I try to find a school somewhere in Virginia or somewhere in the Southeast. I try to find a school with a liberal arts focus, with similar demographics, similar SAT scores, similar racial composition, similar geographic composition, similar anything I can think of, I would try to match as closely as possible. So then I can be more and more sure that any differences I see may be due to the co-ed single-sex difference, not to anything else. If I chose to compare Mary Baldwin students to JMU students, well, there are a lot of differences between Mary Baldwin and JMU other than simply one is co-ed and one is single-sex. JMU is much, much larger. JMU is a public school as opposed to a private school. JMU has a lot more non-liberal arts majors. JMU has there are all sorts of differences. So again, matching people and eliminating as many confounding variables as you can. An advantage of the quasi-experiment, other than the fact that, of course, you can examine things that would be not possible to manipulate, is that you are studying people's natural choices, which under certain circumstances can be important. So it's a more natural, less artificial situation. This is particularly true if you're looking at things like mood or benefits or how somebody likes something. Imagine, for instance, there might very well be benefits of attending a single-sex college, but only for people who choose to go there. If people are forced to go there when they'd rather be in a co-ed college, you might not see a good outcome. So that's the sort of thing. So in a way, a quasi-experiment is going to be a little bit more natural. But of course, the major disadvantage is because the people are sorting themselves instead of being sorted at random, there are always going to be more confounding variables. So it's much harder to be really confident, yes, the difference is due to my quasi-independent variable. So, for instance, let's say you're doing a quasi-experiment and you recruit a group of people who listen exclusively to classical music and people who listen to primarily rock music. And your dependent variable is college grades, and you discover that the people who listen to classical music make better grades than people who listen to rock music. All right. So, again, there may be other differences between people who choose to listen to classical music and people who choose to listen to rock music. For example, about the only radio station that's going to play classical music is NPR. So our classical music listeners are more likely to listen to NPR, which means they are probably going to hear more NPR programming, NPR news, for instance. And so if listening to the NPR news programs affects their grades, that's a potential confound. Maybe the classical music listeners are older, and therefore they're more mature, or they have more disciplined study habits, or something like that. Or maybe they read more. People who listen to class, it's easier to concentrate on your reading with classical music in the background than with rock music, so they read more, or read more diligently, or read more carefully, or something like that. That could also affect grades. And so those are all potential confounds that you would need to control for before you concluded, yes, classical music makes people make better grades. There are other circumstances where it is not necessarily easy to divide people into groups. There are certain categories where it's hard to say, divide people up into discrete categories, yes, no categories. For example, let's say you decided, okay, I'm interested in the effects of watching movies on some sort of behavioral measure, and so I'm going to have to find people who watch movies versus people who do not watch movies. Well, frankly, in this day and age, it's going to be very hard to find people who don't ever watch any movies, unless you maybe go to an Amish community or something like that. Almost everybody sees a movie on TV or Netflix or in a class or something, even if they don't regularly go out to the movie theater. So dividing just movie watchers and non-movie watchers may be difficult because you may find very few in one group. Also, just calling people movie watchers, that doesn't distinguish between someone who goes to maybe 1 or 2 movies a year versus someone who goes 4 or 5 times a week. So they would all be lumped together, and that might not be ideal. So something like movie watching is an example of a variable that isn't easy to characterize into discrete categories. But you still can at times be interested in knowing if there is a relationship or a predictable pattern between the two variables. For those types of studies, you use what's called a correlational studies. This is where you have basically one group of people and you have to measure both variables and look for a pattern of data, look for a predictable pattern. Now, the easiest way to look for a pattern of data is to graph it. So, for right now, we'll just be interested in simple linear relationships. And there are two types of relationships of that sort that you can see, the positive relationship and the negative relationship. In a positive relationship, when one variable goes up, the other goes up. So here's an example of a positive relationship. Hours spent in the library and college GPA. So the people who spend less time in the library here and here tend to make lower grades. You increase your time in the library and your grades ultimately increase. So that would be an example of a positive relationship. Negative relationship is when the scores move in opposite directions. When one goes up, the other goes down. So let's say distance traveled to attend Mary Baldwin College, so the distance between your house or your home and Mary Baldwin College, and the number of visits home that you make a semester. People who live very close may go home very frequently. People who live far away may go home much less frequently. So the data would tend to form a linear line sloping down. That's an example of a negative relationship. If there were no pattern whatsoever, that would be a relationship. There would be no relationship. There would be no predictable pattern, no relationship. So if I graph something like fingernail length and GPA, okay, probably no relationship. Now, your correlational study can also be quantified statistically, analyzed statistically. What you do with that is you calculate what's called a correlation coefficient. We'll do a lab later this semester when we do that. But the correlational coefficient is a number between -1 and 1. A -1 correlation coefficient is a point where it's a line that's sloping down and all the points are falling on a straight line. A +1 is the same thing for a positive relationship. The line is sloping upward from left to right and all the points are falling on a straight line. 0, of course, would be in the middle, and that would be no relationship or no pattern, predictable pattern. Now, a correlational study has some of the same advantages of a quasi-experiment. You can study variables that are not possible, ethical, or practical to manipulate, and it's also a more natural setting. So the disadvantage, of course, is also the same as the quasi-experiment. There are going to be many potential confounds, many confounding variables. And you'll hear psychology majors say this all the time: correlation does not equal causation. So, does spending time in the library cause you to make better grades? Not necessarily. That's a possibility if you've seen a positive relationship, but it also could be that students who are academically talented choose to spend more time in the library, and the high grades could cause the library time as opposed to the other way around. Or some other factor could cause both: your academic ambitions, your desire to go to medical school, something like that could be affecting both. So for instance, here's an example of a positive correlation that certainly is not causal. If you look from day to day, different days of the year, you find a positive correlation between the amount of ice cream consumed nationwide and the number of deaths by drowning. So, does this mean that eating ice cream causes you to drown and your grandmother was right and you can't go into the water after you eat? No, that is in fact a complete myth. There is absolutely nothing harmful about going into the water and going swimming right after you eat. But that doesn't mean, so ice cream does not, as far as we know, make people drown. It certainly doesn't mean that if, for instance, we banned ice cream nationwide, that we would reduce the number of deaths by drowning and prevent drowning by banning ice cream. Of course, the reason that ice cream consumption and drowning correlate is because they're both related to temperature. The hotter it is outside, the more people eat ice cream. The hotter it is outside, the more people go swimming, and unfortunately, the more people go swimming, the better likelihood there is that someone will drown. So they're both, in this case, both of those variables are related to a third factor, temperature. So an example like that sounds kind of silly, that to think, yes, if we banned ice cream, we could stop drowning. But when you see correlational studies published in the media, you see people making this exact logical error. For instance, several years ago, there was a major study in the Journal of Pediatrics showing that teens and adolescents who watched a lot of adult television, a lot of sexually explicit television, were more likely to engage in early and risky sexual activity. So there was a positive correlation between sexually explicit television and early sexual activity. And when this news reports came out and people started going out to various organizations and getting their comments on the study, what was the solution that most people suggested? Well, obviously, we need to take this smutty TV off television, or we need to stop our children from watching this so that they will not be tempted to be sexually active too early. And the automatic assumption that, okay, if we get rid of this TV, we will reduce sexual activity. Makes no more logical sense than assuming that if we banned ice cream, we could reduce drowning. But that is the inferring correlation from, concluding causation from correlation. And the correlation alone does not prove causation. You have to actually show step by step how it is that one causes the other. It could just as easily be that young people who are interested in sex or who are having sex are also interested in seeing TV that has sexual content. So it could be one causing the other or some third factor causing both. So what I would like you to do, and this is the type of essay question you could very easily see on a test sometime, is to think about how you would test a hypothesis with these types of techniques, of these types of studies. So, for instance, let's take this hypothesis. A hypothesis that college students who consume caffeine get less sleep. Caffeine consumption is associated with less sleep. How could you test this hypothesis using either a true experiment, a quasi-experiment, or a correlational study? And then what are the pros and cons of such approach? So I'm going to ask you to stop this recording now. Think about this question a little bit, make a few notes to yourself, come up with your own answer, and then I'll give you my answer on this type of question. Okay, I am now going to assume you have stopped the recording, come up with an answer of your own, and have thought about it. So, if you were going to do a true experiment, you would have to randomly assign some people to take caffeine and some people not to take caffeine for some period of time, at least one day, ideally more. So you would have to recruit a bunch of participants, randomly assign them to one of two groups, give one group caffeine, give one group a placebo without letting them know who is getting what. So you could choose to do this by giving one group caffeine pills and the other one dummy pills or sugar pills, inert pills. You could choose to do this by giving one group coffee and the other one decaf coffee and not telling them which is which. Anyway, but as long, again, ideally you would want them to be blind to which condition they're in. And then you need some way of measuring sleep. You could do this by asking them to keep a sleep diary and report to you when they go to bed, when they wake up. You could possibly put some sort of biological monitor onto them that would monitor their body temperature and heart rate and motion. That would allow you to tell when they were sleeping and when they weren't. So you could bring them into a sleep lab and monitor them on a sleep machine and see how long they sleep in the sleep lab. Either way would be acceptable. But the important thing is that you assign them randomly, treat one group with caffeine, the other group with caffeine, without caffeine, measure sleep, ideally without knowing who is in which group, so the study is double-blind, and then analyze it. That would be a true experiment. Okay. Quasi-experiment would be a little bit easier. You would not have to go out and randomly assign groups and manipulate them and control their caffeine intake for the duration of the study. You could maybe just recruit people, ask them if they are coffee drinkers and non-coffee drinkers, assign them to groups that way. Or somehow find people who do not consume caffeine versus people who do, have two different groups there, and again, do the same sleep measurements. That would be a acceptable way of doing the study. It'd probably be a more natural way of doing the study, but because you're not assigning at random, you could have more confounding variables. For instance, perhaps your non-caffeine users also eat a healthier diet because they're very health conscious. They avoid caffeine and they avoid all sorts of unhealthy things. Well, if diet affects sleep, then you've got a difference in diet that confounds the study. So that would be the disadvantage of a quasi-experiment. It also might be hard to find a group that drinks no caffeine whatsoever. Never has soda, never has chocolate, never has anything with caffeine in it, because caffeine is so common in our society. So the other choice would be to do a correlational study. You don't bother dividing up anyone into groups. You just get a group of people. You measure the amount of caffeine they consume on average per day. You could do this by surveying them, finding out how much coffee, tea, cola, chocolate they consume, figure out how many milligrams of caffeine are in that, and add it up. You could give them a blood test that measures caffeine level in the blood. That would be a very precise measurement of caffeine. But then you'd also have to have the measurement of sleep, and you would then put that on the graph and calculate the correlation coefficient. If your hypothesis is true, you would expect a negative relationship, that the more caffeine people consume on a regular basis, the less sleep they tend to get. So that is the end of the lecture on experimental design. Thank you for your attention.